Hello, I'm Vikram, and I'm a graduate student at Columbia University.
And I'm Sarthika Dhawan, a software engineer at Microsoft. Today we are going to talk about differential privacy and how to leverage Python's PyDB library for it. Let's first discuss what will be our agenda. We will start off with some key concepts of privacy and their definitions. Then we will see what are the risks of handling customer data. And moving on, we will see how simple techniques like anonymizing data won't work in the real world and can still breach privacy of data. So then we will come to mathematically defining privacy and move to differential privacy and how it works under the hood. We will also discuss two key types of differential privacy, and towards the end, we will see how PyDP works with the help of code snippets. Finally, we will conclude the talk with a fun trivia and a Q&A session. Yeah. So, what is privacy? So, privacy is the ability of an individual or a group of individuals to seclude information about themselves, thereby expressing themselves selectively. So, it can be said as the right to control how much information about you is used, processed, stored, or shared. And you should not confuse security with privacy. Security is that controls who can access the data, while privacy is when and what type of data can they access. You can't have privacy without security, but you can have security without privacy. So that is the key difference between these two. Now, there are three main concepts of privacy. First is identifiability. So it refers to the extent to which an individual can be identified from a set of data. So if a set of data can be directly linked to an individual, then that data is known as identifiable. Second one is linkability. So linking at least two data records of the user. For example, if there are two databases and the name of the user, of the customer or user is present in both the databases, we can link those two database and try to and can identify the individual. Then that is known as linkability. So yeah. And then third is traceability. So traceability refers to the ability to track the usage of data over time. So including who has accessed it, when it was accessed, and for what purpose. So this means that the origin, destination, and handling of the data can be traced. So yeah, one example of how data can be tagged to users browsing the internet is the concept of cookies. So cookies, sensitive information like age, salary, gender, address, etc., can be tagged to cookies, and the websites that have access to these cookies will have access to your personal data also. Now, since there is a lot of data we are talking about, and with data comes responsibility of handling it properly. So we will quickly discuss some of the most common attacks that are possible with customers' data. So first is information leakage. It's the unauthorized access to customer data that can occur due to security vulnerabilities in the machine learning model or related infrastructure or due to some insider threats. One example of this can be unauthorized transfer of data from an from a computer or network to an external location. Another example can be there are some type of timing attacks which exploit the timing differences in a system's response to different inputs or events. So, by analyzing the time it takes for a system to respond to certain inputs, an attacker can infer information about the system's state or configuration. Second is snapshot attack. So, it's attacker gains access to the model at a specific point in time, often by taking a snapshot of the model state and then uses that information to launch an attack. And the attack can be used to extract sensitive information from the model or manipulate its behavior. Thirdly, it's membership inference attack, which is in which attacker tries to determine if a specific customer's data was used to train a particular model by exploiting the model's output. And then there is adversarial attacks, which involve intentional manipulation of the input data to cause a machine learning model to make incorrect predictions, which can potentially reveal sensitive information about the model or the data that it is trained on. And then there is model stealing. Model stealing involves stealing a machine learning model by training their own model to mimic it. So they try to mimic the original model and then uh, they can potentially reveal customer data using it. And lastly, it's model poisoning. So in this, attackers inject malicious data into the training data set to manipulate the model's behavior or to compromise its accuracy. So yeah. Now you might be thinking that why don't we simply anonymize the attributes that we don't want to expose, like the private attributes of a user or a customer. So we will see with the help of a case study why it won't work. Consider a hospital maintaining datasets of its patients, and the dataset has these attributes. So for each patient, all these attributes are stored in that dataset. Let's assume that we have a redacted name and SSN, which are like private to each patient, to anonymize the dataset. Now there is a possibility that from the publicly available datasets, there might be some dataset with common information. For example, consider a voters list dataset is also there. It has these attributes, and you will see that zip, birth date, and sex are the common attributes in both these datasets. Um, a unique combination of these can be used to identify an individual. So this is known as the linkability, which we discussed as one of the key concepts of privacy, that we are linking two different databases to uh, find information about a particular individual. This was, in fact, a true incident that happened in which a state governor of US's personal data was leaked with the help of these three attributes, because like his zip, birth date, and sex was the only was combination was the only unique combination existing in both the data sets. And a similar case happened in during Netflix competition of building a predictive model based on user rating data. So they redacted the sensitive information of users like name and other fields, but they linked their current data sets with IMDb's data set, which is a publicly available data set, and through that they were able to identify what rating users gave on a particular show or movie, and thus leaking their personal information. Yeah, so in conclusion, why don't we anonymize data? So anonymizing certain fields may make the entire data set useless and not fit for analysis. So it might happen that you are redacting information which is actually important for analysis, and thus rendering your model useless. Second is, as we discussed, that there might be related data sets available publicly, and statistically studying both the data sets and individual can be easily de-identified. And thirdly, if the data set is large, the type of queries that can be drawn from the data set cannot be predicted. So you can shoot multiple queries on the database, and eventually you will be able to. It's a possibility that eventually you will be able to identify information about an individual. Now, let me hand it over to Vikram to discuss about differential privacy.
Yeah. So now let's come to the core topic of our presentation, that is differential privacy. So to define it simply, basically differential privacy is a tool which addresses the paradox of learning nothing about an individual while learning information about a population. So as we discussed, we should not be able to learn anything particular about any particular individual, but we are still interested in knowing some general trends out of the population. So simply put, it is a formal mathematical formulation of the generic term that we use, that is privacy. So just to explain it properly on the goals and the what the goal of differential privacy is. So imagine there's a data set in which has information about n number of individuals, say Alice, Bob, and Josh. Now, what the goal of differential privacy would be is to make sure that any kind of statistical analysis on the database is possible, but it's possible without compromising the privacy of all these individuals. We refer to a query on the database as any function that I can run over the database. So maybe I can find out, okay, what's the mean age of all the people in the database? So this is a form of a query or a function. And what my aim with the privacy thing is that the query output, like the output of the query, should be indistinguishable between this database and an adjacent database. So I'll shortly explain what an adjacent database is, but simply put, it's a database which is very similar to this database, but it differs in like just one field. I'll explain this in further detail later on. So basically, we'll discuss now what's under the hood. So imagine imagine we have a database containing data of all a lot of people, and then we have an algorithm which does any sort of statistical analysis on this database. Now, what I can do is basically I can take out the information of any one particular individual of this data from this database. So now I have two databases, one with all the people, another one with one less person. And then I can run the same sort of statistical analysis on both of these databases. Both of these queries would result into, like, each query would result in an output. And then if an adversary is able to distinguish between these two outputs, because there is significant difference in the output values, for example, then uh, then basically the adversary is successful in knowing some particular information about that individual. So just for the sake of example, let's imagine this is a cancer data set uh, in which the database stores, okay, if a person smokes, does he or she have cancer? So if in the original dataset there are people who smoke and have cancer, and my algorithm is trying to predict whether smoking causes cancer. Now, what I can do is I can take any one particular individual, remove it, and my query could be, okay, tell me the number of people that smoke and have cancer. So imagine the original dataset gave the value 100, and now I removed one particular individual, and now the dataset gave me a value 99. So technically, I know that the person whom I removed smokes and has cancer. So this is kind of leaking his or her medical data to the public, and an adversary, without having direct access to the database, can still perform two different queries and know any particular information about a particular individual. So this is exactly what differential privacy is trying to prevent, and we have some mechanisms in place for this. So now let's mathematically define differential privacy. Uh, so the definition goes like this: for all pairs of datasets D and D prime that differ in a single participant. So D and D prime here are the adjacent databases that I talked about. So we have these two databases and a training algorithm M. So we call this algorithm M to be epsilon delta differentially private if for all S, and S is the range of M, that is all possible output values of M, if the following equation is true. And the equation is that the probability that a particular query's result on dataset D is less than or equal to e raised to power epsilon of the probability that the same query on the adjacent database, that is D prime, also results in the range set. And there's an additional parameter called as delta. We can discuss the value of delta later, or what this stands for. But loosely, what this means is that the probability that I run a query on database D is the value is similar or very close to the value I would get when I run the same query on a adjacent database, that is D prime. And the parameter delta basically allows for some error in this, because this is a fairly strict condition. Now the values of epsilon and delta are kind of hyperparameters to my model, and I can decide them based on the basis of how much privacy I want, or how much strict my privacy constraints are. So again, let's go one by one. So the parameter epsilon basically limits on how much privacy is the individual comfortable about. Delta is the probability of actually leaking the information. So there are cases in which we define epsilon differentially private algorithms in which the value of delta is 0. And there are cases in which delta is non-zero, in which case we refer to the general case, that is epsilon delta differentially private algorithms. As we discussed, M is any randomized algorithm, that is, it does a query on the database, but also adds some noise so that the outputs are indistinguishable. And S is basically all the range space of this algorithm, or the image of this algorithm. Now, let's come to discussing the two different approaches to differential privacy. Basically, what we know till now is that any differentially private algorithm runs some sort of query on the database, and so we have some sort of statistic. But on top of the statistic, we add some noise so as to preserve the privacy of the individuals in the database. So there are two places where basically we can add this noise. One leads to a concept called as local differential privacy. The other is global differential privacy. In local differential privacy, what we do is we aggregate the data, but before aggregating all the user data or any sort of data, we add noise to the individual level. So each individual record is manipulated by adding some noise, and then it is stored in a central database. In this case, we can call the dataset or the database as an untrusted aggregator because we're not giving the true information, but we're tampering or enhancing the information by adding some noise. The second approach is called the global differential privacy, and in which case the aggregator itself is trusted because it has the original data of all the individuals. But when a third party queries the data, the output of the query from the trusted aggregator is manipulated by adding some noise, so that again the third party is always untrusted, but the database itself can be either trusted or untrusted depending on what approach we do. So usually global differential privacy results in slightly better performance, but however the strict requirement for global differential privacy is that the aggregator be trusted. So because we are giving supplying true information to the aggregator. Now let's come to PyDP and the different sort of algorithms and mechanisms that exist within PyDP. So as Sarthika mentioned, PyDP is a differentially private library implementation in Python. And it has some algorithms which are frequently used in the code snippets, and they'll be also used in the code snippets, which we will show later on. So as the name suggests, these algorithms, for example, say bounded mean or bounded sum. So these algorithms are trying to find out some statistic of the data set, but doing those statistics in a differentially private manner. So take, for example, bounded sum. So this algorithm is basically trying to sum up a particular numerical value in the database, but trying to do it in a differentially private manner, that is by adding some noise. And the way in which we add this noise is referred to as a mechanism. And there are three mechanisms in place, that is the Laplacian, exponential, and Gaussian. So to explain this with the help of, say, the Gaussian mechanism, what we do is there is a database, there's an algorithm. So this algorithm tries to extract some particular statistic from the database. So this is where the list of algorithms we have is utilized. And then there's the second parameter is the noise mechanism. So noise mechanism is adding some numerical noise to the database, but this is not just a random noise. This numerical value is picked from some distribution. And in this case, we have three available distributions, that is Laplacian, exponential, and Gaussian. And we add this noise, and then we get the output. So now all these mechanisms ensure that there is differential privacy maintained in our database. And so each of these distributions would have their own parameters. Say for Gaussian, we have the mean and variance. Similarly, for the other two distributions also, we have some parameters. And we have to adjust these parameters in such a way so as to ensure an epsilon delta value of the differential privacy. So we'll not go into the details, but it's good to know that there are three different kinds of noise we can add to achieve our differential privacy budget. Now let's get to the exciting part of actually going into the code of PyDP and understanding how it works and how a typical algorithm with PyDP looks like. So you might notice the first couple of statements are just importing the necessary packages. The first is where we import PyDP as DP, and then we also need pandas to create our data set and process it in the appropriate format. So here we're working with a salaries dataset, for example, in which we have some individuals with their names and salaries. And obviously it's sensitive information. So the aim is to do some statistical analysis without leaking any particular information about the salary of any individual. So the next few lines are basically where we define the epsilon and delta values. As we discussed, these values are just like we have not picked these values based on some analysis. We have used random values for now just to demonstrate. And now you might notice that we also have some imports, for example, this. So what we did is there's a sub module called Laplacian from which we have imported two algorithms called bounded sum and bounded mean, which we discussed in the previous slide. So simply put, what we're trying to do is the bounded sum from the Laplacian submodule is trying to find the sum wherein the noise is of the form Laplacian. Similarly, mean is also trying to find the mean, but adding a Laplacian noise on top of that. Now, how we use this is as follows. We first define an object of the bounded mean and bounded sum algorithm, and in as parameters we pass the epsilon and delta values, and then to actually compute and add the noise and give us back the result, we do a dp sum dot quick sum and dp sum dot quick result and dp mean dot quick result. So this quick result is basically whatever algorithm you're using, it adds the noise to it of whatever form that we have imported and then gives us back the result. So in this case, our noisy data sum and noisy data mean would be the true sum and true mean. And on top of that, we've added Laplacian noise so as to hide the sensitive information. Now, how is this useful? It's useful because of the noise, it's not possible for me to basically eliminate, for example, Ross from the database, take the sum, add back Ross to the database, take the sum, and take the difference, which would have given me the true salary of Ross. But now because of the noise, it's impossible for me to know what the exact value of Ross's salary is. And this is basically how we added some Laplacian noise. Similarly, you can imagine we can add different sort of noise on in this database to get our bounded sum and bounded mean. Now let's move to a slightly complex example. Ironically, we have used the Naïve Bayes algorithm as an example of the complex algorithm. For folks who are experienced in machine learning, might recognize that this code snippet is exactly like the sklearn implementation of using Naïve Bayes. Additionally, what we're trying to do is we'll go from the top. First, we import the Gaussian Naïve Bayes algorithm from the ML submodule of PyDP. And we have a bunch of epsilons ranging from 0.01, 0.001 to 10. And then what we're trying to do is for all these values of epsilons, we're trying to run Naïve Bayes algorithm on a set of data sets. So for each data set and for each value of epsilon, we're trying to record what's the mean training accuracy and what's the mean testing accuracy. And the way we utilize these algorithms is exactly how the standard implementation of Gaussian Naïve Bayes algorithm you would have done by using the sklearn implementation. The additional parameter that we pass here is the value of epsilon that we're trying to use. And then the CLF is like basically all we do is to fit and test our data on the CLF object that we get by passing the epsilon parameter to the algorithm. And the rest of the thing is exactly as same. We append the training accuracy and the testing accuracy to our global array, and then we do basically the mean training accuracy and mean testing accuracy of these values. So PyDP, the bottom line is that PyDP comes packaged with algorithms such as the Naïve Bayes algorithm, and the way this works is by doing exactly what the Naïve Bayes algorithm does, but in a differentially private manner. Now let's turn our attention to some of the things that we should consider while implementing differentially private algorithms. The first one is using differential privacy when it's not necessary. So it is not applicable to every problem. That is, every problem does not demand the need of differential privacy. For example, individual level analysis. So imagine a bank is trying to find out whether a particular person's bank activity is fraudulent or not. So in this case, the bank actually has the interest of knowing the exact activity that a particular individual is doing. So in this case, differential privacy would not be the right solution because we actually want to do individual level analysis. The second case is when the data set is so small that differential privacy is not a right solution for any sort of analysis to be done on the small data. Uh, the next point is no epsilon is one size fits all. That is, the value of epsilon is dependent upon the kind of analysis that you do on the database, and no one value of epsilon would be applicable to n different number of data sets that we have. So we have to do some analysis before fixing the epsilon value. The third point is not understanding the sensitivity of your data. So sensitivity refers to how much the output of a particular query on a database changes with varying input. Uh, by not understanding the sensitivity of your data, you might not be adding enough noise to the query result, or the algorithm might not be adding enough noise so as to protect the privacy or to meet the privacy constraints of the differential private algorithm. The next point is choosing the wrong differential private algorithm. So there are multiple differentially private algorithms in place, and um, when there's a choice, you also need to invest time in understanding which is the right algorithm for your data sets and for your needs. Uh, the last one is failing to properly evaluate the accuracy of your results. So as we know, differential privacy adds some noise to our data set. So it's natural that the accuracy of your results might decrease with a differential private mechanism. And so whenever you do any differential private algorithm, you must also consider the fact that this can affect the accuracy of your results.
Hello, thank you a lot for your talk. We do have a couple of questions in the Slido and like 3 minutes left. Can you hear me well? Hello.
Yeah.
Cool.
Yes, we do hear you.
Well, actually, we have plenty of questions. So we will start with the first one. How do you ensure that the additional noise doesn't alter the output of the model?
Yeah.
I can take this. Maybe.
Yeah.
So yeah, while we different one goal of differential privacy is that we do alter the output in some way. That is, like, we cannot query individual data sets and get to know the exact information. But to ensure that still analysis and all kind of algorithms work as they are expected to do, we add it in a mathematical way. So in the video, we saw one of the way is adding Laplacian or Gaussian noise. So we can mathematically prove that adding noise from these distribution does not alter the output in such a way that our analysis is different, but it still offers privacy. So the short version of the answer is that we add it in a specific way, and we just don't add random noise.
And another question, would it be possible to infer the distribution of the added noise and thus the true value when executing the same DP query multiple times?
Yeah, so same as Vikram answered the previous question, those noise like Laplacian and Gaussian noise, they are designed in such a way that it becomes a bit difficult to track them back even if we execute the same query multiple times. So yeah, that is how we are able to preserve privacy with those algorithms.
And I think we have the last question. There's more on the Slido if you want to address in our Discord. But for now, due time, one more. How do DP and K anonymity differ with regard to the result of not learning about an individual? And do you see scenarios where this complement each other?
Sure. So, yeah, Vikram, do you want to go or should I?
It's fine.
Yeah.
You can go ahead.
Okay. So basically k-anonymity and differential privacy, they both are important techniques for data privacy, but differential privacy is a bit more advanced technique. In k-anonymity, we basically group individuals which are similar, and then we suppress their attributes to make them like to seclude them and not leak information about them. But in differential privacy, we add noise to specifically uh, like prevent data leak of users. So it's a bit advanced technique than k-anonymity, but yeah, both are useful techniques in this domain.
Oh, so sad. There's 3 questions more, but due to time, we're about to end this. Does anyone really want me to ask? Okay. There's a lot of people, so I will ask one more. Do you preserve the mean important information by adding noise? Do you perform random operations that could be used to track single entries back?
Yeah, I can take this. So the idea is like when we add sufficiently large number of individuals and there's a lot of individuals in our data set, the adding of noise, it's expected that the added noise cancels out. And while like to address it like more concretely, it's not random noise, it's mathematic, like it's based on a mathematical distribution. So again, it comes back to our first question. Because we add noise scientifically, it basically that is all the crux of differential privacy it comes from. So yeah, but basically the large amount of noise cancels out, but it still preserves the privacy of the individuals.
Thank you so much for the talk and for answering all the questions, and thank you everyone who attended.
Thank you.
Thank you.